Lecture 1.8R is about temperature going into calorimetry problems. So we're discussing today how, in fact, we can measure energy going into and out of a compound. What I have in front of you, my friends, in chemistry is the three types of ways that molecules actually vibrate. And this is the motion I'm showing you right here. And I want you to get the idea that when we're talking about molecular motion, we're talking about temperature and the average temperature. Okay, if we go through here, and you can see that energy hits molecules and they move. Okay, forget the graph at this side, but energy, in fact, is a molecular motion. Okay, and that's what I want you to remember from that. But temperature isn't about total energy, it's about the average energy. Okay, here we have some gas molecules traveling at some speed. Okay, if you notice, they're not all going the same speed. Some are colliding and hitting others, and some are being slowed down by being hit in opposite directions. So temperature is not just about motion, it's the average motion. Okay, and if we look at something called a Boltzmann distribution graph, and I'm not getting into these equations, don't worry about these fancy equations, but I want to get to something called a graph here of speeds. And right here is 200 kelvins. Again, don't worry about this stuff here, but to the right we have 200 kelvins. That's a speed that we should know. We should know that's below 0 degrees Celsius. It's a cold temperature. Okay, and this is a range of speeds, the molecular speed. Now this is a temperature, so at 200 Kelvin you have molecules that are going above and below that temperature. So this graph represents an average. So temperature is just an average. You have some molecules going above and some going below. Get that idea? So temperature does not measure total energy, but just an average. And if I play this here, what happens is at 200 kelvins, we have this average at 200. Now if I go to 1273 kelvins, which they're going to go faster. Okay, notice my average went up. And if I go to 222 Kelvin, okay, the average goes up even more. So again, it's just the idea that a temperature is not really a measure of exact motion. It's a measure of the average motion. Very important. All right, so we're back here at an empty piece of paper for good reason. I want to start talking about how we measure energy, okay? And we don't ever measure just energy completely or absolutely. We measure energy changing. For instance, we're going to talk a lot about calorimeters. A calorimeter is just a container that has the environment that we use to measure energy. That environment is usually water. So we have like a styrofoam cup or a sealed container, and we have water in it. And here's my water, H2O. Now we have something called a reaction container. In that container, we put things. For instance, we could put food. Food we know is measured in energy. You guys measure calories, and calories is energy. What they'll do to measure food is they'll take a sealed container. Let me just seal it with the air, okay? And they'll have wires that go through, and these wires will actually ignite the food. And so energy will flow out of the, let me just change my color here, out of the reaction into the water. So we have a flow of heat outward. And this calorimeter is where we measure calories or energy. So we're using water as the environment. Why? Because we have a very, very important definition. 1 calorie, okay, is equal to the amount of energy it takes to raise 1 gram of water 1 degree Celsius. Okay, so they defined a calorie as the amount of energy it takes to raise 1 gram of water 1 degree Celsius. Notice the raising point. It's a change in temperature of 1 degree Celsius, up or down. In the case of the example I gave you, if energy is being released, you should realize that this must be an exothermic reaction and that the energy in the environment's temperature is going up. It's important to know. Okay, now how do we measure this change? Well, we're going to start with the change in temperature. We're going to have a final temperature, okay, and then we're going to have initial temperature. And we're going to subtract those two. So let's pretend that the initial temperature was 20 degrees Celsius in the water. And the final temperature, let's pretend, it became 40. So we raised temperature 20 degrees. The average temperature increased 20 degrees. So it tells us something about that there was a change in energy. Okay, now how do we use that temperature to measure energy? Well, we're going to take that change in temperature and we're going to try to find energy. Okay, total energy. And let me give you a little analogy. Let's say we have an average of a class, because don't forget that change in temperature is an average. Let's say the average in the class is 80. Okay, now if I wanted to know total points, like if I added everyone's test scores together, where would I find that? Well, if this is my average, I'll times it by the number of students, right? If the average of all the students' grades are 80, and I want to know the total points, how do I do that? I take the 80 times the number of students, which is how much I have. Okay, so if there was a class average of, let's say, 80, and there was 10 students, I have a total of 800 points. And that's what we're doing when we measure total energy. We're finding the total points. And we don't have number of students, but what we do have, okay, is we have grams or mass. This mass will tell us how much. So essentially we're taking the mass and timesing it by the average to get the total number of points. Okay? Now the problem with my analogy is that I assume that every student can increase their score equally. And as you know, some students will struggle, some it's easy for, and some don't care and don't work hard. So in case of chemicals, we have another factor. We call it specific heat, because if you're going to have a change, not in test scores, but a change in temperature, you're assuming all compounds change their temperature evenly. And not all compounds do that. Some have a change in temperature that go up quickly, or let me put it this way, some require more energy to increase their temperature than others. Case in point, okay, is let's say you have a metal. For instance, you've got a pot on a stove. Okay, but on that pot, you've got a wooden handle. Why do they put wooden handles on a stove or on a metal pot? Because they know wood is terrible at conducting. It's a bad conductor. Metal is a good conductor. Now, what does that mean? It means that metal doesn't need a lot of energy to change its temperature, whereas wood needs a lot more energy to change its temperature. So this is what called specific heat is all about. It's a factor. And let me help you with this. So let's pretend we have 100 joules of energy going into a compound. Let's say the masses are 10 grams apiece. And we have a temperature change of 10 degrees Celsius. So remember, it's energy equals mass times our change in temperature. And let's say the change in temperature here is 1 degree Celsius. Okay, this factor is where the specific heat goes, how well something conducts. I'll forget my 10 here. Let's change some, okay. Now, 10, I know this is hard to see, but this is 10. 10 times 10 is 100. So we would say the specific heat factor, and let me just get rid of the good conductor that's getting in the way. Specific heat factor, okay, specific heat would be 1 here, because 10 times 10 is 100 times 1. So 10 times 1 is 10, 10 times 10 is 10. That's how to get to 100. Here, the specific heat has to be 10, because 10 times 10 times 1 is 100. Notice, they both absorb the same amount of energy, yet, this one changed the temperature a lot. I don't know what that was. Change in temperature a lot. This one had a very, very small change in temperature. Think with me for a second. If I've got a large temperature change, I don't need a lot of energy to change my temperature. If I've got a small temperature change, I need a lot more energy to change my temperature. That is what specific heat. It's the amount of energy it takes to raise something 1 degree Celsius or some value. So which one do you think would be the metal? Which one has a large change in temperature for the same amount of energy? You got it. This is the metal. And this would be the wood. For the same energy, it has a very small temperature change, which helps us from not burning our hands. So specific heat is a factor in measuring energy. And you should know that things that are terrible conductors, okay, have very high specific heats, and things that are good conductors have low specific heats. So here's our new equation. Energy is equal to mass times specific heat times change in temperature. Now they love to use energy as Q, okay? It's what they symbol for energy. Mass specific heat times change in temperature. Okay, now this equation is given to you in a reference table, so let's look at that. Okay, so if you look at table T, my friends, in chemistry, and scroll down, you will see heat as one of the form of equations they give you, and there it is. Q equals mc change in T. They even tell you Q is heat, M is mass, specific heat, and the change in temperature. There is your formula. So it's right there given to you. Okay, and we need to go also into table B, because in table B they give you what specific heat is for water, because water, like in the first drawing I gave you, is what the environment's going to be. So if you look carefully, specific heats for water is right there. And here it is. It's 4.18 joules per gram per degree Kelvin. That's what it is. Okay? Now what does that mean? That means, my friends, that it takes 4.18 joules to raise 1 gram of water 1 Kelvin. Now Kelvin change and a Celsius change is the same. So that's where we're getting that value. So here it is. Here is our equation. Q equals mc change in T. Now, what gets confusing is people don't know what mass of what compound, what specific heat of one compound, or change in temperature of another compound. And if you notice the drawing that I gave you, okay, water is always going to be our environment. So we're always talking about water. So if it's the Q of the water, it's always going to be the following. Okay, it's going to be the Q of the water equals the Q of the, Grodsky, equal the mass of the water and the specific heat of the water times the temperature change of the water. You don't mix and match. Q for one thing, all these components are the same. Okay, because in truth, we really can't measure the energy of the food because it burned. If it's burning, it's changing its form. Its chemicals are changing, and I can't get a temperature change. So what we're really doing in calorimetry is we're going to do the following. We're going to take the Q of the water and say it's equal to the Q of the food. Now, why are we going to do that? Because food is going to burn, but we know that the energy released is equal to the energy absorbed, conservation of energy. So let's go through some problems and see if we can apply this. Okay, so number 1, how many joules of heat are required to heat a 3-gram sample of water from 4 degrees to 9 degrees? So I start with my formula. Q is equal to mc change in temperature. So they want joules. That's important. And the mass that I have is a 3-gram sample. Okay, specific heat. What am I going to use? Well, I go to table B, and it's 4.18 joules per gram per degree Celsius. Now, I know they had Kelvin there, but we can use that because a change in Kelvin is the same in degrees Celsius. They're the same units. Change in temperature, pretty simple stuff. Okay, we have 9 minus 4, and that gives me a 5. Okay, and this, put in my calculator, is 62.7. Now what are the units? Well, grams cancel. This is supposed to be degrees Celsius, right? That cancels, and I'm left with joules. Okay, pretty straightforward. Okay, notice it's about the water again. Okay, number 2. Now this one's a little trickier for a couple different reasons. You're going to bring in the word calorie. Now I said in table B, the specific heat of water is equal to 4.18 joules per gram per degree Celsius. Now, the calorie, as I just mentioned before, is equal to the amount of energy, okay, which is in this case, I should get rid of the calorie. The specific heat in calories is the easiest number to remember. It is 1 calorie per gram per degree Celsius, because calorie was defined as the amount of energy it takes to raise 1 gram of water 1 degree Celsius. So the easiest number to remember is 1. They give you the 4.8 for joules, but you have to know the calorie, okay? Because that's where the calorie is. It's the amount of energy it takes to raise 1 gram of water 1 degree Celsius, okay? So in this question, they're asking for calories. I'm still using the same equation, Q equals MC change in T. Now watch the difference here. They want to know how much heat in calories. So therefore the specific heat, notice here we canceled to get joules. So we're going to have to use the same thing, except we're going to interchange with this number. So the mass. Okay, let's start with the change of temperature. 10 to 6, 60 minus 10. Obviously that's a 50. Okay. And the mass, well, they gave me a 1.5 liter sample. Okay, now I'm just being really crazy here with this problem, but it's a pretty simple stuff. 1.5 liters, you should know, is 1,500 milliliters, right? And we should also know that density of water is equal to 1 gram per milliliter. So if density is equal to 1, and I have 1,500 milliliters, I should know that this is equal to 1,500 grams, right? If you measure 1,500 milliliters, it's 1,500 grams, because you put 1,500 over 1,500, you get 1. Specific heat, where we're going to have to use calorie, and it's 1 calorie per gram per degree Celsius. Keep forgetting degrees Celsius here. And note, look, everything cancels except for calories. Let's go find that number. Okay, put that in the calculator, and let's just change some, and you get 7,500 calories. Okay, probably have to, at the end, round to 1 sig fig. Here I didn't round to, this is only 1 sig fig for this question, so this honestly becomes 60 joules for 1 sig fig because of these numbers. But let's not consider the significant figures right now. Let's talk about the process. Okay, so I plugged it in and I get 7,500 calories, and they want how many kilocalories. You should be able to convert. So 7,500 calories. I want to get rid of calories. So calories go on the bottom. I want kcals. All right, and guess what? For every 1 kcal, there's 1,000 calories. Small number, big, small unit, big number. We've covered this. So you get 7.5 kcals. Okay, now, how many kilojoules? Well, if you notice, a calorie and a joule differ by 4.18. So if there's a 4.18 difference, okay, we'll do it here. For every 1 kcal, all right, 1, there's 4.18 kilojoules. So I'm timesing by 4.18. What do I get? What does my later of calc tell me? It tells me 7.5 times 4.18, and I get 31.35. 31.35, and that's that's kilojoules. So I'm just having to convert here. Obviously, we're rounding off to, I think, 1 sig fig, so this would be 30 kJ. Okay. All right, moving on to number 3. All right, once you try that on your own. Pause this, and I'll show you my solutions. Okay, so we're back, and you can see that my solutions, okay, are here in front of you. You notice I started by writing the chemical formula, not the chemical formula, using the chemical the formula given for this equation, and notice they gave me in the problem 1 kilogram of water. Notice I had to convert to 1,000 grams, or I converted that to 1,000 grams. Why did I have to be in grams? Notice the specific heat is in grams. So that thing is important. Unlike last year or this year in math, you have to look at your units. It tells you what you have to be in. So kilogram wouldn't work there, it wouldn't cancel. Okay, notice I used the 4.18 because they looked for what? They looked for joules. They didn't put the calorie formula. And of course, the subtraction of the two temperatures gives me my change in temperature. All right, then I just plug it in. Okay, in this problem, there's 3 significant figures, so it goes 69400 joules. Okay, so pause it right here. I'll give you a couple seconds. Try number 4 now. Okay, I'm just going to keep talking until you figure out that you should be pausing this for number 4 now. Okay, I'm done. Pretty fast, right? I'm amazing in my own area. Yeah, okay. Any case, you can clearly see that we had the grams of the water, the temperature change, and I used specific heat for joules because they were looking for joules. Now it was kilojoules, but I solved for joules first. I made sure that all my units canceled, and when I got joules, I just converted my joules to kilojoules. Got rid of my joules, and I put joules in the bottom so it'd cancel and kilojoules on top, and if it's a 1 to 1,000 ratio, right, the smaller unit gets the higher number, and there's my answer. So I'm hoping you're seeing this is pretty straightforward. Okay, now we're going to stop here. I'm going to ask you to do number 5 for homework and number 6. Now, in these two equations, they're a little different. Okay, I mean, you're using Q equals MC change in T, but now you're going to solve for change in T. Now, how do you do that? Well, I would rewrite the equation. Algebraically, I would divide both sides by 1 over MC, so these guys cancel, and divide this by, times this by 1 over MC. Just do an algebra. And what this gives me is change in temperature gives me Q, heat, over mass times specific heat. And by solving for change in temperature, all I'm going to do is plug things in and solve for that. Okay? And you're going to do that for number 6 too. So try to plug that in. Be very careful what the unit is. Okay? If it's milliliters of water, we know the density of water is 1. So that should be 80.0 grams of water. Okay? So try number 5 and 6. Have a good rest of your weekend.